Hey everybody, welcome to Module 4 of Multi-Level Modeling. And this week we're going to start talking about what are called random intercept models, which are the sort of simplest form of multi-level models that actually can give us a lot of cool and useful information. Okay, so I wanted to talk about a topic that I get a lot. A few folks have asked this to me in this class, and every year I kind of get questions related to this. And this comes back to last week's question about null models and what really you should do when you get mixed signals between your ICC, your interclass correlation, and the results of your likelihood ratio test, LR. And that's actually a really good question. So it can happen, but it's actually very rare. Usually, if your ICC is above 0.05, your likelihood ratio test is going to very clearly give you a significant p-value. Just a quick reminder that likelihood ratio test is the thing you get when you run the RAND function after running your null model, or it's also the little test that you get at the very bottom on your stata table, your multi-level modeling results table, where you get a chi-square test with 1 degree of freedom and a p-value. Usually those things will match up really closely, although sometimes, depending on your sample size, you may actually get a case, let's say when the ICC is close, around 0.06, when you may get a borderline likelihood ratio test as well. My advice in that situation is to go ahead and use multi-level modeling. And I call this kind of the belt and suspenders approach, right? If you want to, you should use both if you're worried about whether or not you have an issue with clustering in your outcome. It's always more conservative to use multi-level modeling because multi-level modeling is going to adjust for any sort of a clustering that may exist in your data. And so if you're close, it's always a good idea just to go ahead and use it. Better safe than sorry. But that's a great question. Sometimes you do get sort of conflicting evidence, and it's something you want to weigh. Okay, so we're going to talk a little bit about random intercept models. And just a reminder, last week we introduced the null model, and that's our starting point anytime we want to conduct multi-level modeling. And we learned about how to run a null model, which is essentially a model without any predictors, just one intercept, one random intercept. And we learned about how to calculate an ICC by figuring out how much of the variation in our outcome is happening at the higher level cluster and sort of calculating a proportion of that. And we also learned about this thing called the likelihood ratio test, which I was just talking about a little bit earlier, which basically does the same thing. It runs a model without a random intercept at the higher level, and it runs a model with, compares the two, and sees if sufficient improvement in your model has resulted such that you should probably use multi-level modeling. So this week, we're just going to go a step further, and we're going to talk about how to introduce additional predictors to our model, both at level 1 and level 2. Now, you'll probably remember a model can have more than 2 levels, but once you've mastered the logic behind how level 1 and level 2 sort of relate to each other, I think it's easier then to start adding in additional levels beyond that. Otherwise, things get a little crazy pretty fast. So this week, we're just going to look at adding predictors at level 1 and level 2. Just a little reminder here, a null model has no predictors, hence the name. We only have a dependent variable, which is our outcome, and a clustering variable, which might be classroom, if it's students nested within classroom, or school, or state, or region, or so on and so forth. So last week, we did not introduce any predictors into the picture. So as a result, a null model is only so useful. It's sort of a first step or a bridge to getting you where you actually want to go, which is where you're actually fitting a more robust regression model with more independent variables. But it's a really important first step because it kind of shows you how your outcome is partitioned. Is there a lot of variability at the second level? Is most of the variability at the first level? Do I really need to use this more advanced technique, or would I be okay using something different? But of course, we often have more complex research questions than that, and we want to know what the relationships are between IVs and our DV. And so in that case, we need to add some predictors. And so the nice part is it's relatively straightforward to add predictors at both levels. Now, a quick note of caution. This is often my attitude when I get into a model for the first time and I'm really excited to run everything. Let's take all the predictors and dump them all into the model all at once. And you may have been there too if you've ever played around with running a regression model. It is really tempting to jump right into a more complex model. I think all of us kind of have this itch to want to try sort of the newest, biggest, fanciest stuff in statistical model, and sometimes we skip ahead of some of the steps that will actually help us understand that most complicated model even better. And so that's really the key. And in multi-level modeling, I highly recommend a slower, more methodical model building process. I really think that it will help to encourage deeper understanding of the model that you're running and the relationship of all of the IVs to the DVs. So my advice is to do something like this. Start with a null model, then start with a model that includes only predictors at level 1, then add in any predictors that you have at level 2, and then you can test the parameterization of those predictors by adding what are called random slopes. But we'll get to that next week. We're not going to cover random slopes this week. We're only looking at having a random intercept in our model and then as many types of predictors as we want. And then after we've tested that, you can even add even fancier things like interaction variables, including cross-level interactions, which is probably something you may not have seen before. So you can actually interact higher level and lower level variables at the same time. So you can take a construct that's measured, for example, at the classroom level, and it can serve as a moderator for something that's happening at the student level, which is really cool and really complex. But you don't want to run that until you've sort of tested all of the iterations leading up to it, and you have a pretty clear understanding of how everything is fitting together. Each step of the way, you're going to be checking the fit of the model to see if the model is getting better or just sort of staying the same, or in some cases getting worse if you have a lot of predictors that are not very strong. And so our guide for that, as we learned last week, is going to be are going to be those measures of AIC and BIC. Again, lower is better, and we want to see those things improve steadily over time. All right, so here is our diagram again from Garson, and this just walks through a little bit what we're about to see. So again, I think this is a nice sort of conceptual overview. Ooh, I don't want to jump ahead quite yet. This is a nice sort of conceptual overview of all the things that you can study simultaneously with a multi-level model. And you can actually study 5 different types of relationships simultaneously. So assuming here, this is our DV, a multi-level model first can tell us the relationship between school, or whatever your grouping variable is, and your DV. We can understand the relationship between any lower level covariates or IVs in your outcome. That's relationship number 2. We can understand the relationship between any school level grouping variable and any student level stuff. We can understand the relationship between any school level covariates in our outcome. And we can understand the relationship between any school level covariates and any student level covariates. That's the part I talked about just a minute ago with the cross-level interactions. So there are just a lot of really cool, flexible things you can do, even with a fairly straightforward multi-level model. Okay, so I think I'm going to start here by just walking through a little bit some of the notation. And I think Garson does a nice job of describing how these models work as well. but I would like to get a little bit into the conceptual piece just to have you stick your toe into figuring out into the water a little bit to try to figure out what how this all works and how multi-level modeling really works. So we're going to talk a little bit about notation. I know notation can be kind of scary sometimes, so math notation alert, folks. But I think it is useful to at least talk about it a little bit and try to wrap our heads around it. So here we have the notation for a regular multiple linear regression. So this is an equation for a regression model. We have an outcome here, and notice the notation y sub I. That means this is outcome y for person I in our data set, and that is equal to some intercept, which we call beta 0, plus the impact or the association of several predictors, x1, x2, and x3, and the estimates of those predictors, or the relationship between those predictors and the outcome, is estimated by beta 1, beta 2, and beta 3, and then some individual specific error term, which we call E or epsilon. Whoop, before we get to the complicated stuff. Okay, so that is sort of how the model is set up. We have an outcome that we're predicting, we have some intercept, we have a set of predictors, and we have coefficient estimates of those predictors' relationship to the outcome, conditional on the other predictors in the model. That's the idea of statistical control, that you're controlling for other predictors in the model. So I'm guessing you've seen something like this before. This is the mathematical notation for regression. One thing that you may not have seen or may not have been covered as much in depth is how we think about or parameterize this E or error term, epsilon. Typically, we say something like error is where all of the variation that isn't explained in the model goes. It all gets thrown into an error term. And that's essentially true. That is true. Yeah, the error term, in the way this is designed, any variability in our outcome that is not explained by these predictors or by the intercept is contained within the error term. But the error term is not necessarily a catch-all in that it has specific properties. One important assumption of this error term, and this is sort of how we notate the statistical properties of this variable. This is actually what we call a random variable, meaning it can take on any value, that we assume to be normally distributed with a mean of 0 and a specific variance, which we're calling sigma squared. Okay, I'll say that again. So we assume that this variable is actually normally distributed with a mean 0 and a variance that we're calling here sigma squared or sigma squared epsilon. So that is actually what the statistical assumption is about this variable. Now, if you remember, if you took EDUS 608, you probably learned a little bit about statistical assumptions. In any introductory statistics class, I'm guessing you probably talked a little bit about the assumptions of a regression model. And one of the assumptions of a regression model is that the residuals, right, which is the sort of observed error, that's the stuff that's left, the residuals are normally distributed. I'm underlining this N here. And normally distributed about 0, so that means their mean is 0, and normally distributed with a specific shape, which we're calling sigma squared E. So what we test, when we test the assumptions of a regression model, we're actually sort of making sure that this is true under the hood. We don't always talk about it like that, but that's actually what we're looking for. Now, you're probably saying, why the heck does this matter? Well, the idea of a random variable is very important because multi-level modeling is all about those random variables. What we're doing is we're adding additional random variables to explain variation at different levels. Okay, so coming at you, A little bit more notation. Okay, so here, things got a little bit more complicated, but hang in there. In multi-level modeling, we now have a second random component, and that component is found at the cluster level. And when I say cluster, I mean the level above where your outcome is being measured. So if you have students nested within classrooms, you have a random term at the student level, and that's this thing right here, this epsilon. But now you also have a second random term that's measured at the classroom level, and that's right here, and that's mu. So you've added a second random term to your equation that needs to be estimated, and that is to explain variation that happens between classrooms, because we know that the classroom may be a meaningful piece of how all this works. So now we have two random terms in our model, and we need to estimate, we need to get estimates of both of those variances. So we have this sigma squared, which is the individual level variance in our outcome, in the unexplained portion of our outcome, I should say. And now we have tau, what we call tau 0, in this case, because it's an intercept. And tau is the unexplained variability at the cluster level. So when we look at our output and we get those random components, those variance estimates that I'll point out in just a little bit, that's what we're actually talking about. Those are the things, those are the quantities that the software is actually estimating. It's estimating the variance. Notice it's not estimating the value of this. It's not estimating the value of epsilon or the value of mu, because we assume that on average, the value of that thing is actually 0. So what we're most interested in is not the value of epsilon and mu. We're interested in to what extent they vary. And so we're estimating the variance of those terms. So that's what I mean when I talk about variance. So what that means is we actually get a little two-level, which I'm circling over here to the left, a two-level equation for our new model. So before we had y equals beta 0 plus any predictors plus e. Now we actually have a two-level equation. And this square right here on the left side, this is actually the two-level equation for a null model. This is actually what we ran last week. So what it's telling us is yij, so that's our dependent variable, say math scores, for student I in school J. Notice that notation. So now we were talking about IJ. Before we were talking about just student I because we weren't taking into account the cluster. So now student I in school J, that is a function of some intercept that's tied to the school J, plus some student-specific random variability, okay? And then we actually go a step further and we define this intercept. So this is not what we would do in regression because we only have an intercept and an error term. Here we're actually taking that intercept and we're pulling it apart too. So beta 0j, you can almost draw a little arrow down to here. So beta 0j is actually composed of some fixed intercept, which we now call gamma 0. That's the old beta 0 in original regression. Now gamma 0, because it's at the second level, plus mu 0j, which is the school or classroom specific component of our random variability. Okay, so to pull it apart, we end up with a fixed intercept value, gamma 0, plus a individual level variance, which is actually sigma squared, but it comes from epsilon. And we end up with a school or higher level variability, which is mu, but actually, again, we're estimating the variance of mu, so it's tau. Whew, wow. I know, a lot of moving parts there. And I totally understand if you're like, oh, okay, some of this is not entirely matching up, that's okay. I just want to show you a little bit about how the math is working under the hood and what we're actually doing when we're doing multi-level modeling. We're accounting for variability by including a second random term that helps to explain some of that variability. So this would be how you would represent mathematically the equation for a null model. Okay, one more slide of notation. That's it, I promise. Okay, so now this week we're going to talk about adding predictors. And when we add predictors, it gets a little bit more complicated, but it's not too bad. So now we're starting to add predictors. So here's our level 1 equation here. And the level 1 predictors are the x's. So x1 ij, x2 ij, x3 ij. And their coefficients are the betas. So beta 1, beta 2, and beta 3. So these are student level characteristics if we're talking about students nested within schools or classrooms. Okay, so these, all the predictors here are modeling student characteristics. The level 2 predictor, which I'm going to show you one, is represented by a W, and its coefficient is a gamma, just like the intercept is now represented by a gamma. So this is a school or classroom specific predictor. So these are things that change according to what classroom you're in. So maybe this is classroom size, or maybe this is the type of school you're in, or maybe this is the amount of funding that the program you're in receives, or so on and so forth. These are things that don't change at the student level, but change at the higher level. Now, for now, we're going to treat all of our predictors as fixed. So the only extra random component we have down here is our random intercept, which we're calling mu0j, which is also right here. And we're only estimating 2 random components, an individual level random component for the intercept and a school or classroom level random component for the, also for the intercept. And we're calling that actually tau. Okay, so when we start to add random components to our slopes, beta 1, beta 2, and beta 3 here will change a little bit. For right now, we're treating them as fixed, so we don't have any additional random components being added, but eventually we'll get there. All right, so I totally get if this seems a little bit overwhelming, and I'm not expecting you to have to digest this and immediately be able to put it in practice and, you know, do this kind of stuff in your sleep. The idea here is just to show you how, starting with something like regression, right, a simple linear regression, we can slowly start to add components and things can start to be more flexible, and you can really start to estimate a very flexible and complex model to answer your research questions. But it all starts with understanding these random terms and what's going on at the first versus second level. And once you get a hang of that, you can really start to expand and build on this in some really, really cool ways. But you don't have to know how all of it works to be able to run and interpret multi-level models. That's the nice part about the software. The software has allowed for us to fairly quickly and easily estimate these things. And so, yeah, eventually we want to know exactly what's going on if we're going to run a multi-level model. But for now, just sort of getting a sense of how these things work is our goal. Okay, so I'm going to do another video, short video, where I talk through the output that we're going to get in today's demonstration lecture in kind of more detail. I think that might be helpful. So I will provide that shortly, but that is your intro to conditional random intercept models. Thanks.